This is a brief demonstration of Gurobi Compute Server. What is Gurobi Compute Server? You can think of it as Gurobi Optimizer as a service. You deploy this software on a machine of your own or a virtual machine. It could be in-house or in the cloud. And then it solves models for users on other computers, users or processes, batch programs, anything that uses Gurobi. It gives you the full power of the Gurobi solver with a few limitations on callbacks, but it seamlessly integrates into the client's workflow. So if you look at this file on the right side of my screen, it's showing a license file for Gurobi Compute Server for the client side of the equation. This means that if I put this file on a client machine, it will begin to send all of its jobs to, in this case, some host name, some computer name, some host name. That could be a fully qualified domain name or just a local network name if you prefer. So it makes it very easy to switch someone from using Gurobi on a local license or some other kind of license to submitting its jobs to Compute Server. And so the applications themselves see no change. You can do this with APIs, but it's not necessary. And so this Gurobi Compute Server lets you manage multiple jobs by providing a queuing system. It first takes jobs by priority. It's a number that you can assign. I'll demonstrate that in a moment. Higher priority jobs come first. But if you use defaults and don't set a priority, or if you have two jobs of the same priority, then it's first in and first out. You can also cluster Gurobi compute servers. If you have enough jobs running concurrently, then it's a good idea to have two of these or three or however many you need. And then the clustering is something proprietary that Gurobi provides, very easy to do. And once you've done it, then you can balance, the jobs are balanced between the compute servers and the jobs are spread out across all of the machines. There's a REST API for doing really customized kinds of management. And so if you think of a scenario you want to support with your Gurobi compute server, it's probably possible. It's a very thorough sort of API. Now, communication for Gurobi compute server is done over HTTP or HTTPS. And that's all the communication, the clustering, everything is all handled this way. And latency is rarely a problem. It's surprising, I think, but it turns out that it's just, for most problems, the latency of the network connection has little effect on the solve times. So let's have a demonstration. First, I'll show the classic case where I'm using Gurobi here on a local license, and I just have a Gurobi prompt using interactive shell. But I can switch that very easily over to Compute Server by switching the license. Here I have a license file already defined, like the one in the previous slide, that points to a particular machine on the network. And having done that, I'll show you what I have for a license file. And now it will send its jobs to this machine called desktop, whatever that is. So now if I run gurobi.sh, you see, oh, before I do, I should start the server. It's actually already running. There it is, running on port 80. And so now when I start the server, it should run on the compute server instead of on the local license. And that's what happened. You can see I'm running the compute server in this case as an interactive process. That's not typical. The default is to run it as a service on Windows or a daemon on Linux. But in this case, I'm running it interactively so you can see the log as we go along. You can also see in the client session that the compute server was used, and we get a job ID, which is very useful for diagnosing things afterwards or looking at usage patterns later on. So I'll leave this one running. Let's see what happens when I try to do it again from another machine. If you look at these title bars, I've labeled them job 1 and job 2. Job 2 now will invoke Gurobi's, and it's already configured to use the compute server. And so it should run on the server as well. Let's see what happens. And it does. So again, I've got a job ID. It's different. This one ends with 8B4D. Previous one was something else. And that's fine. It allowed me to run two jobs because I configured it that way. This is something, a very important consideration when you're using compute server. There's a parameter in the configuration file. Now this one for compute server is called grbrs.cnf. And anyway, I've defined mine to have a job limit of 2. I could say 2,000 if I wanted to, but I wouldn't want to. This is important. So let's take a canonical case where you have a compute server with 8 cores. You're going to want to limit the number of threads each machine has if you're doing concurrent jobs. In this case, I set my job limit to 2. I would set threads for each of the jobs to be 4. That way, I'm not oversubscribing the cores on the compute server. Let me show you that. So we have 2 sessions running now with a job limit of 2. When I try to start a third job, it shouldn't allow it. Something should happen. In this case, I'm not doing an interactive shell because I wanted to show you, I'm using the command line version of Gurobi. I wanted to show you the threads parameter in use. When this job is started, use only 4 of the physical cores on the machine where it started. And in this hypothetical case, you can assume that I've done some testing and found that this particular model solves well with 4 cores and doesn't really benefit much from more. This is an experiment you'll want to do on your own models to figure out the best way to divide the power of that machine. So let's run this and see what happens. I'm in a queue. It's a blocking call. In this case, I'm in Gurobi CL, but if it were a Python program, the startup of the Python program, when I import Gurobi, would begin to wait in a queue. There's an object called an environment that's created regardless of the API you're using. And when that is created, it's a blocking call as long as the queue is active. So let's kill this one and see what happens to the previous one. I'll move this over to the left. We should see job 3 kick off. Let's see what happens. And it does. I now have only 1 job running. Let's start it again. So I have 2 running now. And I'll put job number 3 into the queue because I want to show you one more feature of this that I mentioned previously. Job number 4 now is another command line Gurobi with threads equal 4, but I'm setting a priority on it. The default priority is 0. You can set priorities to -100 or all the way up to 100 integer values. And so if I set a priority 11, it becomes a higher priority job than this job number 3. And so when I free up one of the part of the job limit by quitting this one of these 2 jobs should start. And based on what I've told you, the higher priority job should be the one, even though it was submitted after the lower priority job. Let's clean up the screen here so you can watch this happen. So when I quit this one, we should see job number 4 on the far right kick in and job number 3 continue waiting. Oh, I forgot to type enter on the job number 4. Let's start our test over again. So for job number 2, we'll start Gurobi, and we'll put this one in the queue, and we'll put this one in the queue. Now they're both queued. Now we can quit this one, and we should see job number 4 go first, and it does. It just wasn't in the queue yet previously. So when that finishes, job number 3 should kick off and solve, and everything should be handled just as we designed it. The problem running in job 4 is a bit long, so we'll move on with the presentation. So in the demonstration, I tried to show you that you can serve more users better with compute server. Users still work locally, which is really nice. I can work on my laptop and still get the power of some big machine you've deployed Gurobi server to. Typically, you'll go for a machine with at least 8 cores, lots of or very fast CPU clock speeds, because that really helps solvers, and lots of memory. The benefit is that the user's machines, if they're doing other things, aren't going to be slowed by Gurobi, which almost always grabs all the cores on the machine and uses them. It can slow down other things that a desktop user might have running. Queuing serves more users with one license too. So if you have a machine with, say, a single use license, a lot of organization has to go around making the most out of that license. People have to take turns using it and so forth. With the queuing, nobody worries about it. They submit their jobs and go on about doing other tasks while they're waiting for their solve to come back. Same thing happens for production systems. If you can allow for some lag time in the solves, a production system can solve a lot more problems in a given day if you're queuing up jobs and making the most use of it. And also, using a dedicated machine provides reliable solve times. If I'm working in a graphics application of some kind while I'm trying to solve with Gurobi on my laptop, that's going to affect the solve times, no question about it. So that's a big factor. So job management provides all these priorities, and there is a special override priority too, which lets you put things right at the top of the queue. And it also keeps a job log history if you tell it to, so you can manage usage patterns and study them. And you can solve, in short, more models with fewer resources using Gurobi Compute Server. Fewer license resources from Gurobi, but also fewer hardware resources. It's a good way to maximize your use of your Gurobi licenses. If you have any questions, please contact your Gurobi account manager at sales@gurobi.com or contact support at support.gurobi.com.